I'm John Batchelor, Hotel Mars Episode N. David Livingston, Dr. Space, joins me. David, this is very exciting because we're talking about the most famous planetary body in the history of poetry, the moon. Good evening to you, David.
Good evening to you, John.
We're not traveling to Mars. We're going to stay with the moon because where did it come from? Ask yourself, why do we have such a large moon? It's one of the largest in the solar system. It balances our planet. We don't wobble. We have seasons. We have tides. The beautiful moon. Where did it come from? We welcome a very careful researcher and scientist, Bill Bottke, principal investigator. He is at the Institute for the Science of Exploring Targets team at the Southwest Research Institute, and he and his team have put together some extremely impressive details, experimental details that confirm a story I was told just like a fairy tale. Bill, a very good evening to you. The fairy tale went like this. Once upon a time, the Earth, hanging in the heavens all by itself, had no moon. And a Mars-sized planet going by very close hit the Earth. Bang. And the remains of that collision spin off, and the detritus forms the moon. Now, that's felt like a fairy tale. You and your colleagues have pursued that fairy tale, and you found data to support it. A very good evening to you. Congratulations. The animation at NASA is wonderful. What did you find to confirm that fairy tale? Good evening to you.
Well, thank you very much. Well, one of the interesting things about forming the moon is that we think it's sort of a natural byproduct of how you make the planets. We think originally the planets started with lots of small things, and eventually, and this is all in the inner solar system, and eventually through gravity, through collisions and the rest, they grew much larger things. And at the end game of this, maybe about 100 million years or so, the Earth, the proto-Earth I should say, received its last major impact. And we think this is the event that produced the moon. But the question is, when did this event take place, and how precisely does it go? And so teams of scientists from around the world have been looking at this issue. Now, one of the things we wanted to find out is how old is the moon? When did the moon actually form? And this has turned out to be a very difficult problem because the samples we brought back from the moon, the oldest ones, have been heavily beat up. They've been affected by impact events, have been affected by volcanism, and so they're very hard to interpret, and so there's been decades of arguments about this. But one of the things our team did, and one of the things I just published recently, was this following idea, is that when you have a very large collision to make the moon, not only do you make a moon out of a disk of debris that's created around the Earth, but that same event launches a lot of material completely out of the Earth-Moon system, and it starts to fly around the inner solar system. Now, it's not a significant amount of stuff compared to the mass of the Earth. It's only maybe about 1% of the mass of the Earth, but that's actually a lot of stuff. That's many tens of times more than the current population of our asteroid belt. And this stuff goes around and it starts to beat up on everything that it can, including some of the oldest objects we have in the solar system, namely there are asteroids in the asteroid belt. When they hit these asteroids, they create impact craters. They produce impact heating. And we think by looking at some of the meteorites that have fallen on the Earth today, which we think are derived from the asteroid belt, and the fact that these events, they've been impact heated, we can actually see the signature of this giant impact in the inner solar system on material coming from the asteroids. And they suggest that our moon formed almost 4.5 billion years ago. And that time seems to line up with a lot of other evidence we have from lunar rocks and some other work that people have done. So it's an interesting story, right? You can think about, it's almost as if you have an explosion, you have collateral damage. You have material flying around, destroying buildings, maybe killing people and such. But then investigators go in, and they look at all the damage, and they try to piece together how the explosion took place. And in the process of doing that, by looking at all the collateral damage, they can often say a lot about how that collision took place. That's sort of what we're doing in the inner solar system with this giant collision that took place to make our moon.
David?
Good evening, Bill. Assuming this hypothesis is correct, how does it all end up as our moon in orbit a couple of 100,000 miles above Earth? What was the process that created that?
Okay, so to make our moon, what happens is first you have a giant collision. The collision produces essentially a giant disk of debris around the Earth immediately after the collision. So you can think, so you've seen Saturn's rings. Think about the Earth having very massive rings filled with material, which is, several percent of an Earth mass or so. And then what happens is this material starts to try to consolidate as best it can, and it starts to form a moon sort of towards a couple. If you go out just a little ways away, it starts to form a moon, and then that moon starts to interact with the Earth and the disk gravitationally, and it moves away. But in the process, the disk is still trying to create mass, and so little moonlets are leaving this disk, and they're ultimately accreting on top of the moon. They're joining together, and so we think after a few hundreds of years or so, we actually have a moon, which is about the same size as our moon. It's just a little bit closer. And then over the next 4.5 billion years, it slowly moves out by tidal forces, forcing the moon to move away from the Earth. In the process, the Earth is spinning ever so slowly. So it's treating the rotation of our Earth to move farther away from the Earth.
So, and this happened in the first 100 million years of the solar system.
Yes, we think if the estimates we have are right, it formed about almost 4.5 billion years ago, or about 100 million years after the very first solids formed in our solar system.
That's well before what we call the Great Bombardment, which was after this. So that would not have changed the relationship between the Earth and the Moon.
No, it wouldn't. What's interesting about this is that after you've created the moon, you now have a target which can receive impacts. Mm-hmm. Now, the moon is filled with impact craters. We see large impact basins that make a lot of the face of the moon. We see lots of smaller craters. And the oldest ones the origin of them has been something of a mystery. It's conceivable that the same event that produces the moon, that creates the moon out of the debris, in the process of sending some of this debris all across the solar system, some fraction of this material comes back. So some of the earliest bombardment of the moon could simply be debris from the giant impact event coming back. The younger basins, younger big craters, we think come from an event called the Late Heavy Bombardment. That happened about 4 billion years ago, and the story of that is somewhat complicated and interesting, but there's certainly a suggestion that something very dramatic happened in our solar system to destabilize comets and asteroids and send them flying everywhere. So they hit the moon, they hit the Earth, they hit Mars, and there's a record of that on all these bodies.
David?
Correct me, but it seems that things with the moon have been somewhat, is that a good word, stable for many billions of years? Or can we assume that the moon is always going to be stable orbiting Earth?
Yes, as far as we know, as far as we can tell, the moon is quite stable around us. It's going to continue to evolve outward. Right now, the moon is slowly moving away from the Earth. Again, as we sort of trade the rotation of the Earth for the orbit of the moon, so we're actually moving it slowly away. It's going to continue that way, I think, for billions of years, and eventually it'll reach a point where it can't go any further, and then it'll actually move a little bit closer to the Earth. But in general, we're talking about a moon which isn't going to do very much other than sort of look pretty in the night sky.
We now have a probe, not Dawn, around Ceres, the dwarf planet. Can we expect to find the treatise of this impact on a dwarf planet like Ceres? It's conceivable. The thing you have to keep in mind with Ceres. So Ceres is the largest asteroid we have in the asteroid belt. And it lives in sort of a population of impactors. So Ceres is covered by craters. Most of those craters are coming from impacts just from asteroids in the asteroid belt. It is possible that some of these could be from other events. Okay, they would be somewhat special, but they also may be lost in the noise a little bit. So you could ask the question, well, how in the world did we ever figure out the moon-forming event debris actually hit these objects? It turns out that material coming from the inner solar system hits the asteroid belt at extremely high velocities. And those velocities are what you need to produce high amounts of heating. So you get impact melt and other things. So if we go to Ceres and find certain craters where it looks like there's been lots of heating, lots of melt produced, and other things, that may be an indication that those impactors didn't come from the asteroid belt, but they came from outside the asteroid belt. And those craters look different. You can discern that from Dawn, for example, with the cameras there.
They would actually look very much like every other crater, but in the bottoms of the craters, they may have impact melt, or they may have evidence that some of the craters, so I should take a step back. Ceres is a very interesting world in terms of its composition. Right. It may be much more water-rich. There's many suggestions that consider the possibility that Ceres may have an ocean underneath its surface. It may have an ice.
And that would mitigate the search because it would have a newer surface, perhaps.
it might have a newer surface. But you can imagine if an impact produces lots of heating, you may actually change the chemical nature of the material in the bottom of a crater. You can imagine it being changed. Maybe it's dehydrated in some fashion. In other cases, you may actually, if you have enough heating, you may bake the water out, and you change the minerals in some fashion by allowing water to go on the surface in some fashion. So it could be looking for a certain number of craters like this, we might be able to see something. And we're all, greatly anticipating all the results from Dawn.
Right.
They should be coming back in the very near future, and we're going to probably revolutionize our ideas about this very large asteroid.
David, the moon is still magic, even though we now know it's confirmed where it came from. Do you agree, David? It's magic.
Magic, and our literature wouldn't be the same without it.
And can't we say that romance is often a result of people bumping into each other, David? Is that fair?
High velocity, high heat impact, absolutely.
Dr. Bill Bottke, Principal Investigator, Institute for the Science of Exploring Targets. He's at the Southwest Research Institute. His team, the website at NASA, has a spectacular animation from a colleague of Dr. Bottke's, R. Canup. I thank Doctor. I'm John Batchelor. This is a Hotel Mars episode N.